Good morning.
Good morning, everybody.
Can you already hear and see us? I don't know. Maybe you can just write us a message in the chat.
Yes.
Somebody's writing. Very nice.
Good. We're trying to wait and see if there are more participants. We have already quite a lot of people.
Yes.
Okay, perfect.
Perfect. So sound is here, video is here. Perfect. Okay. So good. Welcome to our, I think it's the fourth now.
Yeah, the fourth.
Number 4 of our webinars. So it's actually number 2 because we are doing them in German as well as in English. And we got quite a lot of registrations for the webinar of today. It's like over 50%, so it's a really nice number.
Exactly. So we don't have 50 people logged in yet. So we're trying to wait a bit if some more people are going to turn up. But yeah, I think we're going to start.
Yes, we're starting with the introduction because it's not the relevant things for the actual theme topics. All right, so let's go. All right, today's agenda will be a bit of introduction of ourselves, who we are, and then we will talk about the basics for nanofiltration as well as the application range, something about energy efficiency, and also a little perspective. What are we going to do? What are the future plans for webinars, academy, and everything? All right. So we will talk about our hosts, your hosts, me and Birgit, and about working with EduDip, but we already see that you can handle the chat, so and also about the objectives of the webinar today. So me, myself, I'm René Scholz. I think many of you already know me or know the name René Scholz. I'm responsible for the Herco Academy and also for the technical support and claim processing and customer service of Herco. I'm meanwhile 10 years experience in water treatment, and for the last 5 years I've started with technical trainings mainly. And last year I also got a certificate of the TÜV, so the notified body of Germany for the trainer.
Yeah, and me, I'm Birgit Fabricius. I'm responsible for product management in Herco, and I have 13 years experience, first in wastewater treatment, then in water treatment. Yeah, I'm gonna lead you through the more theoretical part of the webinar, let's say, and then René is going to talk about the practical stuff like application of nanofiltration.
Yes. All right, so in the Herco Academy, we do a lot of trainings, but mostly it was trainings with the customers here at Herco. So this is a quite new way to reach our customers and your customers, of course. So before we did like 40 trainings, and now due to Corona, we didn't do any this year. And so we decided to start with the webinars and the online training courses. And we are continuing with this because it's having a great resonance and our customers are happy with this new communication.
Yeah, and especially for people outside Germany, it's a good option because you don't have to travel so far. So it's easier for you to...
Yes. All right, so working with EduDip, as you have probably seen, we have the chat function, and you also have the possibility to use your hand symbol. So this is for using to say us if you didn't understand anything or you have any other remarks. So we will just jump right into the next slide. The microphones and cameras of the participants are deactivated just to don't have any resonance or anything, echoes. So the webinar will actually be recorded and will be provided afterwards. You will find them on the PWG website and also on our website. To communicate with us, just send simply a question in the chat and we will try to answer it. And yes, questions will be answered after each chapter, and if it's a really deep question, then we will clarify it afterwards with the email.
Exactly. And if we are going too fast, please don't hesitate. Just send us the hand signal. Say, okay, I haven't understood it. And then we just go back over the topic.
All right. So The objectives are actually to get to know the digital learning process. It might be something new for many of you. And in the technical part, we are reaching for basic understanding of the membrane processes and also know the differences between nanofiltration, reverse osmosis, and also ultrafiltration, as well as the areas of the application. And we will have some examples of this and also talk about the energy efficiency. All right, so to get started into the topic, we will do a short survey and ask you what are the characteristics of nanofiltration. So it should pop up on your screens right now. So there's either a stronger retention of monovalent ions or a stronger retention of divalent ions, or no pressure needed.
So we have 2 votes, 3 votes.
Yeah, don't
Going
worry.
Up quickly.
Yes,
it's not a test.
It's not a test. Yeah, it's just to reactivate the knowledge you're having. So we get a lot of answers. That's good. All right. Still increasing, so we get a bit more. All right. So we will present now the results, and it looks good. So we will continue, and during the slides you will know the answer.
Okay, so we'll jump right into the theoretical part, let's say, or the basics of nanofiltration. We'll start by having a look at generally the basics of osmosis and membrane technology, just very quickly, because most of you will know that already, but just to bring everybody on the same level. Then we'll go to a comparison of nanofiltration with similar technologies, let's say, ultrafiltration and reverse osmosis. We'll have a look at a special feature of nanofiltration, which is ion selectivity. And we're going to have a look at an interesting effect, the Donan effect, and what all this means for the retention of nanofiltration membranes. So to start, very simple example from daily life. Maybe this has happened to you. Maybe you have a garden with a cherry tree. You want to pick the cherries, they're ripe, and then it has rained overnight, and suddenly a lot of cherries are split. Why does that happen? What happens here is you have rainwater outside on the cherry, and in the inside of the cherry, you have also water with a lot of dissolved substances, mainly sugars, but also salts, for example. The water on the outside of the cherry is pretty much clean without any dissolved salts. And it has a higher chemical potential than the water inside. Now, the skin of the cherry is permeable for water, but not for sugars or salts. So what happens is, in order to equalize the potentials, the water will flow from the outside of the cherry to the inside. Of course, you get a higher volume, and at some point, the skin cannot contain the volume anymore, and it splits. We're going to have a look at the let's say, chemical explanation on the next slide. So what did happen here? We saw an example for osmosis. The cherry skin in this case is a semi-permeable membrane, which is permeable for the solvent, in our case water, but it's not permeable for the dissolved materials. In this case, mainly sugars, but can be all kinds of organic molecules and salts. In osmosis, we always have 2 solutions with since only the water can cross the membrane, an equilibrium is reached not by the movement of dissolved material, but by the movement of water. So water flows until the chemical potential in the 2 solutions is equalized. In daily life, we have some examples that you have probably seen already. For example, you cook sausages. If you cook them for a long time and the cooking water doesn't contain any salt, it can happen that they split as well. In this case, it's a similar effect as with the cherries. You have a lot of salt in the inside of the sausage, not in the outside water. So water flows into the sausage until the skin splits. There is a different example with salad, where the movement of water is in a different direction, let's say. In a salad dressing, there are lots of salts. in the salad leaf itself, there's not so much salt in the cells. The same goes, for example, for cucumbers. In this case, when the salad leaf or the cucumber is immersed in the dressing, salt will stream out from the cell into the dressing to lower the salt concentration. And what happens is the salad wilts. That's why one always should add the dressing just shortly before eating. For example, in medical applications, we have this effect if we have an infusion. Normally, if infusion is done just with pure water, what would happen is that the red blood cells would simply split as well or burst because there's an inflow of clean water into the cells. In order for this not to happen, we use always a physiological salt solution for infusions. This is because a physiological solution has the same salt concentration that is present in the bloodstream. These are real-life examples. Now we go more to the technical side. Here's what you see, what happens in osmosis, what we have talked about just now. On the left-hand side, there are two compartments initially with the same water level. We have a higher concentration in compartment 1, which you can see already with the color. What happens here is that the water flows from compartment 2 to compartment 1. And the process is in equilibrium when the water level in compartment 1 is so high that the hydrostatic pressure counters the osmotic pressure. Now from this to reverse osmosis, it's just a small step. So this is what you see on the right-hand side. In reverse osmosis, we turn around the process. So we start also with one compartment with a higher concentration, C1. And this time we apply a pressure to this compartment. And when the pressure is higher than the osmotic pressure, the water is going to flow from compartment 1 to compartment 2. So from the more concentrated, from our feed, to the permeate. The required pressure depends on the salt content, because this salt content will influence the chemical potential, of course. Now we see how this looks really in a reverse osmosis unit or plant. So here we have a feed water, which was our original compartment 1 with a higher concentration. We have a high pressure pump, which produces the pressure we need to overcome the chemical potential, let's say. Then we go through an RO module, and the water flow is split into permeate, practically clean water with very, very little ions, and a concentrate, which goes to the wastewater connection, which is the remaining water and most of the ions contained in the feed. Sometimes we have to have a return recycle of the concentrate. This is simply because the RO modules require a certain flow velocity so that we don't get a super high concentration of ions right next to the membrane, because there's almost no water movement. So we need a minimum water movement, let's say. And if that is in some cases not possible with a feed, we have to recycle the concentrate. This is done sometimes, but not in all the plants. Okay, the variants, let's say ultrafiltration, nanofiltration, reverse osmosis, work similarly. And this flow scheme is practically the same for nanofiltration and for reverse osmosis. Okay, now let's look at what is really the difference. So why would we choose to use nanofiltration anyway compared to reverse osmosis or to ultrafiltration? Here we look at a scale that shows us, let's say, the separation efficiency. So we start with 100 micrometers on the left-hand side. This is still within the optical limit of our eyesight. So this is, for example, the thickness of a hair, what you see indicated here, and you can still see these particles. As we move to the right-hand side, these are very, very small distances now. So we start at about 100 to 1 micrometers with conventional filtration, which can remove suspended solids, for example, pollen, the larger bacteria, or single-cell organisms like yeast, which have a relatively large cell size. From there, we go to microfiltration, which is in the micrometer range, where it gets the name from. This is about 1 to 0.1 micrometers. Here we can still remove suspended solids, really. Let's say very small particles, like soot particles. We already remove viruses in this range. The same goes for the ultrafiltration, which is still has a better separation efficiency. But you can see that here we still remove basically dissolved compounds, dissolved solids. So we have hygienization, a removal of bacteria and viruses here, but we do not have a removal of salts, because you can see that the size of dissolved salts is about 0.1 nanometers. So with an ultrafiltration, you would be able to remove, let's say, colloidally dissolved particles. You would remove suspended solids, but not salts. Now we reach the range of nanofiltration and reverse osmosis. Nanofiltration separates particles down to 10 to 1 nanometer. From this nanometer range, it gets its name again, nanofiltration, and it can remove already a lot of organic compounds, the larger ones. If you go to very small organic compounds, such as, let's say, methanol, ethanol, you have to move already in the range of reverse osmosis. You can see here that dissolved salts are partly removed by nanofiltration, but not all of them. And this is going to be something we look into in more detail in the next slides. But nanofiltration already removes quite a lot of dissolved salts and achieves separation efficiencies that are pretty good. Reverse osmosis, there we are really in the range where we remove practically all the dissolved salts that are present in the feed, down to metal ions, really up down to the atomic radius. Now, we have different efficiencies here. This also results in different, let's say, operation conditions, different pressures. This we can see on this slide. If we look at ultrafiltration, where we remove no ions at all, you can see here that the retention for sodium chloride is 0%. We have a low pressure, so 0.1 to 5 bars. That's not much. If we look at nanofiltration and reverse osmosis, the pressure gets a lot higher. So nanofiltration is about 3 to 20 bars. Typical range, let's say, around between 5 and 10. We see that there's a retention of salt, sodium chloride. We have 20 to 60% retention. This is a lot more than ultrafiltration, obviously, but a lot less than reverse osmosis, which removes practically all the sodium chloride present. On the other side, reverse osmosis also has a higher pressure, from 10 to 100 bars, depending on the salt concentration in the feed. So if we want to do a seawater desalination with reverse osmosis, we would rather need 80 bars. If you want to do drinking water, we would probably rather in the range of 10 bars. Okay, that's the retention. Now let's have a look at the ion selectivity. We have seen nanofiltration removes 20 to 60%. Now that sounds like very little, really, right? You don't want a membrane that removes 20% only. But nanofiltration is special in the sense of that it is selective for ions. You have monovalent ions, so with one charge only, like chloride, for example, which can mostly pass the membrane. That's why you get retention rates only in the range of 20 to 60% here. And then you have divalent ions, which are mostly retained by the membrane. So if you look at, for example, calcium or magnesium, you have retention rates higher than 90%. This is because the processes of separation for nanofiltration are quite complex, more complex than reverse osmosis, where we simply think about the membrane as a complete layer where molecules get diffused and pass the membrane like this. In nanofiltration, we have micropores. So we have membrane with negative charge on the surface. You can see this indicated here. The membrane is shown in blue, and you see the negative charges. And this membrane has also micropores. We have organic molecules here, which are too large to pass the pores, so they are retained by the membrane. Then we have also anions. For example, we have divalent anions, so 2- here. These anions are simply rejected by the membrane because of the negative surface charge, and they cannot pass the membrane, mostly. there are the anions with monovalent anions with only one charge. Here the rejection efficiency or the rejection is not so strong, so these ions can partly pass the membrane through the pores, as you see. Then we have cations. You would say, oh, great, they are attracted by the membrane charge, so they should pass very well, right? Not quite. The divalent cations enter the membrane really, but they are retained in the pores because they bind in the pores to the negative charges of the membrane, and then it's hard to dislodge them. The same as I've told you about the anions goes for the cations with respect to monovalent and divalent ions. So monovalent cations will pass the membrane easier because they're not bound so much to the surface charges. Divalent cations are bound and retained. Okay, what happens then is that basically we retain most of the divalent ions, cations and anions, and many but not all of the monovalent ions can pass. So let's go to the next slide. Apart from this pore structure, we have a very interesting effect, which is a bit surprising. This is the Donnan effect. Donnan was a British chemist who lived about, well, pretty much 100 years ago. He discovered the effect. What happens here is we have an important influence from electroneutrality. Electroneutrality means the charges in one solution have to be always neutral. So you cannot have more positively charged particles than negatively charged particles, or vice versa. When we have a solution of only sodium chloride, as you see here on the top, let's say, you would have a certain passage over the membrane. So let's say 60% are retained, 40% pass. Or 40 retained, 60 pass. Depends a bit on the membrane. Now, into this solution, you drop additionally some sodium sulfate. Now, the sulfate ion is divalent. It has two charges. That means it is pretty much completely rejected by the membrane and cannot pass. Now, if nothing changes with the retention of sodium chloride, what we would get here is an imbalance in charges, because sulfate with its negative charge stays on the feed side, and sodium and chloride are mostly passed to the permeate side. Since this cannot happen, the retention of the cations, monovalent cat and anions, is changed. So the cations retention is increased because you need positive charges to balance the negative ones of the sulfate. And the retention of the monovalent anion, so chloride, is decreased. You don't want additional negative charges on the feed side. You already have too much. What happens here is if the concentration of sulfate is high enough, you see a very strange effect. So chloride can cross the membrane even against the concentration gradient, which means you could have a higher chloride concentration in the permeate than in the feed. This will happen only if you have a lot of divalent anions that cannot pass the membrane. But it is an interesting thing to keep in mind, because this is something that would not happen with a reverse osmosis membrane. Okay, now we look at the big picture, all the retention mechanisms. So we have one steric exclusion, which is what we talked about for organic molecules. Molecules are simply retained because of their size. So larger organic molecules cannot pass the membranes, they cannot pass the pores are very small. We have dielectric exclusion, so that's because of a hydration shell, like this example here in the middle with a molecule that has a hydration shell. It would have to, or an ion, it would have to shed it to pass through the pore, but the energy that is needed to shed the hydration shell is too high, so it will stay on the side of the membrane. We also have the Donnan effect, as we explained just now, where electroneutrality plays a part in retaining some ions that otherwise would have passed the membrane. If we look at the grand picture, let's say, how does this influence the retention in total? The retention increases with increasing pressure differential. So increasing pressure on the feed side will increase retention. Sounds strange at first, right? We would expect the opposite. what happens is the water flow over the membrane is practically convective, we say. So water flow like in a river. The water flows through the pores, and the water flow depends on, let's say, the driving force, which is the pressure. We increase the pressure, we have more water flow through the pores. The salt passage is a bit dependent on the pressure, but not so much. Mainly it is dependent on electric attraction or rejection, so it does not depend very much on the pressure. What happens if we ramp up the pressure is that water flows faster, or there is more water flow, but there is just a tiny bit more salt flow or salt passage. So in the permeate, we have a lot more water and just a bit more salt. So in total, we have an effect of more retention and less passage of salts with increasing pressure. If we have a higher feed concentration, so higher salt concentration in the inflow, the opposite happens. If we have a lot of ions, for example, some cations can bind to the membrane and mask the negative charges so that anions are not rejected so strongly anymore. So in that case, with increasing feed concentration, the retention is going to decrease. So we will find more salt on the permeate side. Okay, this goes for all the membranes, but we have also different nanofiltration membranes from different suppliers. And here we see on the next slide how this influences the results. Here we have a comparison of the retention. We compare one reverse osmosis membrane, which is completely on the left, with 3 different nanofiltration membranes, which you see here. We have on the x-axis the molar mass. So here we look at organic molecules, which are different in size. And we have on the y-axis the retention as a percentage. You can see that, for example, for a molar mass of 100 gram per mole, that the reverse osmosis already has quite a high retention of 90% or more. This happens for nanofiltration membranes only at a larger size of around 200, let's say, grams per mole. And you can see that these 3 membranes from different suppliers have quite different retention efficiencies, really. So there's one membrane that is at more or less 50%, while the best one is at more or less 90%, so pretty near to reverse osmosis. It's a general effect that the types of membrane will differ quite a bit. This does not mean generally that, let's say, the membrane here that is lowest in retention is a bad membrane. That can mean that simply this is a membrane maybe that has ultra low pressure requirements. And if we have the right application where we want just a partial retention and very low pressure, this can be the membrane for us. If we want a higher retention and maybe a bit higher pressure, maybe the 3rd nanofiltration membrane, which has already higher retention, would be the better one. So we can, to have a summary, let's say, we can say the retention is different for different nanofiltration membranes. Doesn't mean some membranes are worse than others. It means they are maybe useful for different applications. We have seen that the mechanisms, the separation and retention mechanisms of the nanofiltration membrane are more complicated than reverse osmosis. That does not necessarily mean that the handling is more complicated, because the handling is really quite similar. But we have to keep it in mind to see that we can have some effects that we wouldn't expect if we know only reverse osmosis, like how is sulfate retained, how does chloride pass the membrane, and so on. So after this general introduction, so that you know about the principles of nanofiltration, we will go more to the applications. And this is where the interesting topics start, because you will see where you can use them.
All right, so before we will do another survey, so just to check if you listened to her. So what is the actual working pressure of nanofiltration membranes? So we have 1 to 2 bar, 5 to 10 bar, and 50 to 100, or 200 to 1000 bar. Yeah, we have a really nice trend, so looks really good. All right, so 5 to 10 bar is the typical range, so it goes from, let's say, what did we say, 3 to 20?
Exactly,
I think is the complete range, but the usual operating range is between 5 and 10 bar. All right, thank you. So, all right, so the application range. So we will have a short overview over the applications, for example, partial softening of drinking water, as well as hygienization for cooling and air conditioning. And the most common one for us is the recycling of reverse osmosis concentrate. And then we will have some overview about examples of installations. All right, so nanofiltration is applicable for partial desalination, as well as removal of divalent ions, so partial softening, and also for the removal of microorganisms and the reduction of pressure, and also the recovery of reverse osmosis concentrate, which leads to a reduction of water consumption, of course. All right, on this picture, we see a classical Herco KR unit for the concentrate recirculation, and it's quite easy to see that it is one because we have different sizes for the pressure vessels. So on the bottom, you see 8-inch membranes and vessels, and on the top, 4-inch membranes, and those are indeed the nanofiltration membranes. All right, so here we see a map of Germany. I don't think that we have many German participants, but anyway, we can do this for all the maps on the world. So here we see the German hardness over the map. So we see the blue parts with really hard water, and then the gray parts with really soft water. So this is just to give you a feeling that we have really different hardnesses for different areas because of the mountains and everything. So. All right, so we are using the nanofiltration for partial softening of groundwater with high total hardness, and it is often used for smaller plants. So this means for below 70 cubic meters per hour. So this is really big for us.
But for municipal plants, probably relatively small.
Exactly, yes. And so far we have over 38 municipal plants in Germany as of 2010, and the largest one is in Dienstlaken. It's a town in Germany, and was built in or expanded in 2017 with a total flow rate of up to 1,100 cubic meter per hour. So it's a really huge unit, but not from Herco, unfortunately.
Unfortunately, yeah. We would have liked to build that.
So the advantage of partial softening of the drinking water is, of course, that the residual hardness is desired. So we don't want a complete hardness removal in normal drinking water because it tastes different, and you get corrosion in the piping and everywhere. So we want some residual hardness remaining in the system in the drinking water. And we have a big advantage, that's hygienization compared to other filtration methods. And we have the separation of organic substances like humid acids, colors, and micropollutants. So, and also the reduction of specific ions, so sulfate, if it is necessary for the customer.
What is maybe interesting is that nanofiltration can be a really good option here if you have to remove several classes of pollutants, let's say. So if we need a softening, and we also have to remove humic acids, for example, that give the water color, or there are micropollutants because we take water that actually is filtrated from a river or whatever. And in this case, nanofiltration has a big advantage. It can remove all of that in one step.
Yes, compared to ultrafiltration or anything.
Exactly.
Yeah. All right, so the more common one, let's say, is the hygienization, or not more common, I don't know. So used for humidifier, cooling units and cooling towers, and treatment of feed and makeup water. Some of you maybe already know the UEDZ series. It's basically a hygienic reverse osmosis of Herco with a self-supplying pressure unit, so you don't have the permeate tank in between the applications. So it's a direct feed of the application afterwards. And we can also build this unit as nanofiltration units. So as you guys probably know, we are limited to the size of 1,200 or 1,500 liters per hour with the EDZ series, but we can build it with nanofiltration for bigger sizes, of course, then. All right, so the advantage is, of course, we have in the cooling systems, we want a bit of residual hardness. And the other advantage is, like we said, the entire water flow passes the membrane and we have the hygienizations. And this is because in the application, you usually need some residual hardness. So you have to blend the permeate with some feed water again, and this will result in the things that you removed with the membrane, you're putting in again with the blending. So it's better to have the nano actually. So, and also you're having more cycles of concentration with the cooling towers.
Exactly.
Yes.
Then if you use the conventional softening, so if you use conventional softening, maybe have, let's say, 3 to 4 cycles. If you would use nanofiltration and you also remove quite a bit of salt,
yeah.
probably you can use up to 7
to
cycles.
10 maybe. Yeah. Mm-hmm. All right, so the most common one is the water saving function that we are knowing, and this is the recycle of the concentrate of the reverse osmosis. So normally we would use the concentrate of our reverse osmosis membranes and directly drain it with, let's say, 25% of the feed water usually, and 75% is used as permeate to our customer or to the consumer. What we are doing in the concentrate stage sterolysis now, we are using this concentrate that is produced by the reverse osmosis, and we feed them to nanofiltration membranes, and we use the purified water of the nanofiltration membrane and refeed it into our feed water in front of the pump. So this produced water has, in most cases, a better quality than our feed water, and the concentrate of the nano will be drained. So with this system, we can increase the yield from normally 75% up to 85 to 90%, which doesn't sound much in this schematic, but it's really a big difference. And we will see this in the next slides where we do a small calculation for this. All right. The main advantage also for the nano is because we know the pressure is really low for the nanofiltration, so we don't need a second high pressure pump like in permeate stage systems. So we can directly feed it only with the concentrate pressure that is remaining from the membranes of the reverse osmosis stage. All right, so we will do a small comparison of 2 units. So it's a UOD and D. So it's a standard low pressure unit with reverse osmosis membranes, and a UOKR. So with the concentrate recirculation over the nanomembranes. And we are taking an example with a capacity of 6,000 liters per hour. And we increase the yield, like we just said, from 75 to 90%. And we calculate this with a running time of the plant of 12 hours per day. And the water cost may be different in your country, but we calculated with the German general €2.50 for fresh water and €2.50 for the wastewater. So as we can see here on the y-axis, we have the invest, the actually invest in euros, and on the x-axis, we have the time where it creates the cost. So actually we can see a cut after 3 months. So this means that after 3 months, the additional invest for the KR system has already paid off. And from this moment, in the 3rd month, it actually prints money.
And you can also see something that I think is very important for the discussions with the client. You can see the original investment, which is, let's say, around 20,000 for the normal conventional reverse osmosis. And let's say 20% more, probably 25% more for the KR plant. Now, of course, that sounds like a big investment to the client, but if you see already what you have used up in money for water costs after 1 year, you have more than recovered it. Yes. And if you think about 2 years, 3 years, 4 years, it's really a big difference. This is always interesting if you use drinking water, which are a lot of our applications. So then you have to pay for the water, plus you have to pay for the wastewater.
Exactly.
And this 2.5 is, I think, not exaggerated. At least in Germany, it's a typical cost.
Yes.
So if you have some similar cost structure, it's really worth it for you to look into a KR plant instead of a combined reverse osmosis nanofiltration plant instead of a conventional reverse osmosis plant.
Exactly, yes. We have a question. Can you repeat what does UOND and UOKR? Yeah, it's actually a German a German indication. It's called UO is for Umkehrosmose, which means reverse osmosis in German, and ND is standing for Niederdruck, so that means in English low pressure. So it's reverse osmosis low pressure, and UO again reverse osmosis KR for Konzentratrückführung, which means in English concentrate recirculation.
So it's not as intuitive in English as it is in German, unfortunately. Let's see, another question. Okay, good.
Okay,
all right.
All right, let's continue. We are building many of the KR units. So in the last 8 years, we built over 70 KR systems. So it's a huge number, but we would like to increase that, of course. And starting from next year, the units will be equipped with a PLC from Siemens.
Exactly.
It will be S7
1200.
Yes, exactly. So with a new LCD display, and there will be different sizes also.
Yeah,
I think
we will equip the smaller plants with a smaller display, 4-inch, and then the larger plants with a 7-inch display. Because simply for the smaller plants, the price increase is larger proportionally, as a proportion simply. So there we go for a simpler solution. And for the larger plants, it's really worth it to have a proper 7-inch display where you can see the whole D&ID, the schematics, because we had a lot of clients who were asking for the system to be integrated in PLC systems of the client to record all the data and send all the data to the central system. And we think it's really worth it, especially for the larger plants, to have a proper data monitoring that is really comfortable for the client.
All right. So next point, we are saving operation costs via the nanofiltration stage and FU as well. So FU is also a German word for Frequenzmeter, so it's a frequency inverter actually. So
I think it's usually called variable frequency drive.
VSD,
yeah. So
that's just, again, the German, our type, how we call it.
Exactly. Probably we'll have a webinar about that maybe later this year.
Yes, exactly. So we will do another webinar in September or maybe October about energy efficiency of pumps and variable speed drive pumps. All right, so here we see an example of an installation in Ludwigsburg, so near to Herco. And this is for drinking water treatment for permeate production of 2 times 115 cubic meters per hour. So it's a quite big unit for us. And we have a yield of 80% at 12 degrees Celsius. So it's quite cold water. And we also had the task, let's say, of reducing the nitrate content.
Exactly.
So the raw water had 26.9 degrees German hardness. So I don't know what French hardness this will be, but you guys probably know. So it is also with 38 micrograms per liter in nitrate, and we reduced it to 6 degrees German hardness. So it's a quite big decrease, and also to 22 milligrams per liter of nitrate. All right, so in this picture you see the schematics. So it looks quite big, but this is just to give you an idea of what we did there. So we have the reverse osmosis stages here on those 2 parts. And then we have the stages with the nano membranes, and we are not draining, not recycling the permeate of the nano stage as we did with, or we do with the KR systems. We are actually blending the produced permeate with the nano permeate. So it's a bit different than the standard application, but also an interesting solution for the design.
In this case, the blending makes sense because the customer didn't want a very low hardness or a very low salt content, because obviously for drinking water, that wouldn't be too good either. Yes. For taste, for a lot of other stuff. So in this case, it was not necessary to return it, but just a blending of the very good permeate, let's say, from the reverse osmosis stage, and the not so good permeate in terms of hardness and salt from the nanofiltration was enough to reach exactly the parameters required.
All right, so here we have some examples of installations and also the industries where they are installed, so you get an idea where you can ask your customers if you already have some. So we sold in Ireland 10,000 KR for the paper industry and another 5,000 KR for a detergent producer. So what's a detergent?
Soap, let's say, or
right.
shower gel.
So another one at 25, so a big one for the dairy industry, and also 8,500 for a sports car manufacturer. You still have to tell me who it is.
I know. It's a well-known one, very well known.
All right, for the 6,000, we had a big data center for computers, and then a 3,000 for cosmetics industry, and a bigger one for the animal feed industry. And then also a really big one in Belgium, maybe it was one of you, for a potato processor. All right, so we will do another survey. So which function is actually the most important or most relevant for you? So, all right, so you see we have either saving water or saving energy, then the hygienization or the partial softening. So what do you think is the most interesting one for you? You can choose more of them if you want.
Okay, so it's quite distributed. I think we had that yesterday in the German webinar too.
Yes.
And I don't remember if yesterday it was more.
I think it was.
It was similar, right?
Yeah, I think so too, yeah.
It was a bit more saving energy, I think.
I think so. All right, so here we see the results. So yesterday was mainly saving water, like here too, but I think it was a bit more. But the idea was similar to yesterday, but I think hygienization wasn't that big yesterday.
That could be, yeah.
All right, thank you.
Okay, so after showing you the different areas of application, we want to do one, let's say, case study for one of these 4 advantages, and we have chosen energy efficiency. So here we want to show you a comparison between reverse osmosis and nanofiltration to see how nanofiltration compares in terms of energy efficiency. We're going to have a look at the scenario first. Maybe next slide. So this is was a real case, a real life inquiry. This application is cooling tower makeup water, and the client wanted permeate production of 20 cubic meters per hour with a yield of 85%. So they had, I think, probably a high water cost, so they didn't want to have so much concentrate. The water has a total dissolved solids content of 630 milligrams per liter. Normally, our plants can do up to 1,000, but 600 would be around pretty common range, let's say. And the temperature for the design was 15 degrees Celsius. The hardness in the water, in the raw water, was 20 degrees German hardness, or 355 milligrams per liter calcium carbonate. And we have considered for the comparison first of all, conductivity and calcium in permeate, so the quality. We have considered the pressure of the high pressure pump and the corresponding energy consumption. And of course, we have had a look at the most important thing, energy costs. For calculating the energy costs, we have considered blending, because what happens here, you need water for a cooling tower. It's not necessary to have completely demineralized water, right? So if we would use a reverse osmosis for treatment of the water, we would blend afterwards anyway. And to have a proper comparison, not to compare whatever, apples and bananas, you could say, in this case, we are looking at energy consumption of the reverse osmosis, but also energy consumption of reverse osmosis if one part of the water we get from raw water with blending, so that we achieve in the end the same hardness and conductivity in the permeate as with the nanofiltration. So then it's really an exact comparison. Okay, let's have a look at the configurations. So we have calculated this. We have used the same configurations really of the plants. So hydronautics modules, which are the ones we use usually. We have also worked with other suppliers though. And in this case, it would be for the reverse osmosis membrane type SPA1 and for the nanofiltration SNA1. We use in both cases 17 modules. And it is as it's usually done with a calculation of the membrane supplier's calculation after 3 years of operation. Okay, now if we look here at the results, you can see that we have a certain reduction of dissolved solids. So in the permeate of the reverse osmosis, you go from 630 to 37, 38 milligrams per liter, which corresponds to a salt retention of 95%. This is already for reverse osmosis a bit low. Normally we would have more than 97, or we warrant more than 97, and you can get really in the beginning more than 99%. This is because here the focus was more on having a high recovery, so the 85% yield, and not so much on the retention. But even if this would be done with a different system, it's the same similar result. Okay, nanofiltration, we see that here we have 150 milligrams per liter TDS, so that's quite a bit more. And we have salt retention of 80% compared to the 95. Pretty representative for nanofiltration, I'd say. If we have a look at the high pressure pump, you see that this lowering of, let's say, retention corresponds to really a big lowering of the pressure. So we have here 7.6 versus 12 bars. That's quite a bit less. And correspondingly, the specific energy consumption, of course, also goes down from 0.6 to 0.38. This is energy consumption in kilowatt hours per cubic meter of permeate produced. Okay. So if we have a look at the next slide, here we have compared the energy consumption, here shown as kilowatt hours per day, assuming that the system runs the entire day. We have first the value for reverse osmosis, which is no surprise, the highest. Then we have the value for reverse osmosis with blending. This is 19% lower, simply because 19% of the water doesn't cross the reverse osmosis, but is delivered directly via blending. The nanofiltration, even if the quality of the water of RO with blending and nanofiltration is the same, the nanofiltration shows you that you have even more energy reduction. So the energy consumption compared to reverse osmosis is 37% lower. And even if you look at the blending version, it is still quite a bit lower than the -19 for blending. Okay, so you can see in this comparison really that if we look at the energy costs, it's really worth it to use nanofiltration instead of RO with blending. And it has the increased advantage that all the water is going to pass a membrane, so you will have less input of microorganisms from the feed water, which is a good idea for cooling systems or humidifiers or other systems like that. Okay, to sum it up, everything we have talked about. Okay, so we have shown you quite a bit on the basic chemical side, on the processes. Don't be scared. It looks complicated, but we want to stress nanofiltration is really, really similar to reverse osmosis in operation and design. So as René has shown you also with the plant looks the same. Yep. If you look at a plant, nanofiltration or reverse osmosis, at the first look you won't know because the membranes are just the same. The operation, how you operate it, how you clean it, how you install it, all of that is really, really similar.
Yes.
And it's also really a smooth transition from reverse osmosis to nanofiltration. That's why a lot of people also say nanofiltration is, let's say, wide or not so fixed reverse osmosis membrane. Yes. Okay. We can use nanofiltration for either partial desalination, for softening, for hygienization, or as a stage in an RO unit to recover concentrate and thereby save water. We can use it also for saving energy costs because of the lower pressure. And we have a question here, I think, about energy costs.
Yes. Is savings on energy costs with nanofiltration high enough to have the extra costs for nanofiltration membranes?
Depends a bit on each particular case. In general, most probably, if you look, it will have an advantage at some point. The question would be, do you have, so nanofiltration membranes can be a bit more expensive. That's true. It's not such a huge difference, really. And if you have a look after a few years, you will definitely have a payback. The question would be when. So yes. If you're happy with a payback period of, let's say, 1-2 years and you're within that range, great. If it's a payback after 5 years, maybe the client will think about if he wants to do that.
Yes.
So in general, for the cost savings, it would be important to look at the water analysis, to look at the energy costs of the client also, because one client in Germany, or let's say in Europe in general, will not have the same energy cost as somebody in, let's say, Kazakhstan.
Absolutely.
So it depends a lot on the boundary conditions. Yeah, you can, but you can definitely reduce the operation costs significantly, especially if you have the typical water costs or energy costs, but let's say of more than 10 cents per kilowatt hours that we have assumed now. Yeah. So definitely there can be quite a large reduction. We have a lot of experience. We have built, especially with KR plants, really at least, let's say, 9 per year. And we have a lot of experience with purely nanofiltration plants as well. So we're happy to advise you. I think one point I just want to put in, because it's a question that we got a bit earlier, nanofiltration is really comparable to reverse osmosis. So in terms of, let's say, what damages the membrane, what shouldn't be in the feed, it's really, really similar. Somebody has asked about oil. Oil would be problematic. So oil is problematic for reverse osmosis. I mean, you know that better than me from the service part. And it would be just the same for nanofiltration. So if you think about membrane lifetime, if you think about what shouldn't be in the feed, you can really transfer your experiences with reverse osmosis. One of the questions that will come, or first question maybe, okay, where are your nanofiltration systems in the catalog? There are no nanofiltration systems in the catalog for a very, very simple reason. We derive them from our reverse osmosis systems. So basically, the plant is not that different, which is good for you also when you work with a plant. When we get a nanofiltration inquiry, we adjust the reverse osmosis units that we have already, and then we can offer you exactly the nanofiltration you need for your applications. This is simply to keep, let's say, to keep our catalog simple and not to include, let's say, 10 more series of nanofiltration, which would be a lot of work, and
exactly.
It's easier for you to inquire, and then we will adjust the reverse osmosis plant. We always recommend to have a frequency converter, because especially when you don't have a water analysis, it makes sense to have a bit of flexibility with a pump. And in general, if you have a special case, if you have general questions, we're always happy to advise you.
Exactly. Eric, so you will receive a certificate afterwards and also a handout. So like we said before, the recording will be provided on the PWG site and as well on our website. So if you have any questions, just write us an email, or you can also call us. Maybe not tomorrow.
Especially me, because I will be on holidays.
Exactly. All right, so we have another question. Do you have an experience with ammonia removal by nanofiltration, pH of 7.15 to 7.4?
Okay, there we would really need the complete water analysis, I think. In general, ammonia removal shouldn't be super high because it's monovalent too. But if you have these specific conditions with a pH, I think it would be really useful to have the complete water analysis to give you a qualified answer. So feel free to send us an email with the analysis and we'll respond and have a look at your project.
Exactly.
Okay, let's see some more questions.
Right. We have somebody writing. We will wait. So we have nothing left to cover, so you can pop your questions if you want.
And yeah, otherwise, we hope you have nice holidays in August. Probably most of you are just at the start of the holiday season.
Yes.
We're gonna be back in autumn, let's say around September, with more webinars, more invitations. And if you have a special topic that you want covered or where you would really need information, also feel free to send us an email, because we're very happy to see the input from your side, what webinars would be really useful for you.
Thank you. All right, so we have something left, just free surveys. So we would be happy if you answered them. It's just about the schedule and the overall explanation. So the first one is the course was too short, on point, or too long. All right.
Oh, great. Everybody agrees. That's nice.
Looks really great. Thank you for that. All right. So everybody said was on point. Thank you very much. All right. So we have another one.
It's only 3 in total, huh?
Yeah, so not much. So this one is about the competence of the trainer. So how good we were, good, mediocre, or bad.
Don't hesitate. We need the feedback.
Yeah,
it's
we
okay.
need feedback. So it's not criticism. It's just potentials for us to create better webinars.
Exactly.
All right. This looks brilliant too. Thank you for that.
Okay.
All right. And we have one last
question.
one. And this is, your goals have been reached. You agree or partially agree or don't agree. And if you don't agree, just let us know, send us some emails and we will check.
So it's totally fine if you don't agree, because it's always problematic to cover the basics as well as the advanced part, because some people see the webinar and they know all the basics. Exactly. And they want to have advanced topics. Some people want to really look into nanofiltration and haven't worked with this topic at all before. So it's a bit hard for us to find the right balance between basic stuff and advanced stuff. And if you have, let's say, advice on that, or you want specifically an advanced webinar or whatever, feel free to drop us a line.
Exactly. All right. So this looks good too. You partially agree or agree. So we are happy with that. Thank you for this. And as said, if you have any questions left, feel free to send us an email. And we will just stay for a couple more minutes if there's anything else left, if there are any questions, and then we will finish.
Okay. Thank you very much for the participation. We wish you nice holidays.
Yes.
And we hope to see you back in September, October or so.
Exactly. All right. See you guys.
Good. Thank you very much. Have a nice day.